Hi there, this is Professor Shannon Gracie. Today we're going to be covering logarithmic and exponential equations. We are working out of the Precalculus Enhanced with Graphing Utilities text by Sullivan and Sullivan. So let's go ahead and start out by doing this warm-up here. What I want you to look at is, what is the denominator for both sides of this equation? Right, it's 5. So doesn't it make sense that this numerator would have to equal to this guy? You got it. So let's solve it. This is true only if x squared minus x is equal to 2. And that is an equation that is quadratic in form. So we'll just get 0 on one side. And factoring, we have x minus 2 times x plus 1 is 0. So x minus 2 is 0, or x plus 1 is 0. So x would be 2, or x would be negative 1. You're all done. Oh, got a little crazy there. Okay, so now we go to solving exponential equations by expressing each side as a power of the same base. So recall that if some base raised to the u is equal to the same base raised to the v, then u has to equal to v. So then rewriting so basically you make sure you look at your equations and then you see what kind of form they're in, and if you can, you rewrite it in that form. And then you set u equal to v and you solve. Okay? So, a couple of examples. And by the way, this doesn't always work. You know, we're going to learn a few other techniques in this section. So you have to be able to strategize when you look at these problems as to what technique will be the best. And there's more than one way often to solve the problem. So here, what do we get? Do you see that we can rewrite this equation as 10 raised to the x squared minus 1 is equal to 10 squared? So now that we have the same base, we can equate the powers. So we'll get x squared minus 1 is equal to 2. So we'll get x squared, actually, we can just do this. X squared is equal to 3 when you add 1 to both sides. And then we could square root both sides, and we would get x is equal to plus or minus root 3. And you'll see if you check the equation, you'll get the same, it will check out and you'll get equivalent results. So negative root 3 and positive root 3 were the two solutions. All right. Why don't you pause the movie and give part B a try and see how you do. Okay, let's see how you did. Notice that both 4 and 8 could be rewritten as powers of 2. So this is equivalent. 4 is 2 squared and 8 is 2 cubed. Now when you raise a power to a power, what do? You multiply. So this is equivalent to 2 raised to the 2 times quantity x plus 1. And this guy on the right is equal to 2 times 2 raised to the 3 times 3x. So we'll get 2 to the 4x plus 2 is equal to 2 to the 9x. So equating the powers, we will have 4x plus 2 is equal to 9x. Subtracting 4x from both sides, we'll have 2 is equal to 5x, and dividing both sides by 5, 2/5 is equal to x. And we're done. Okay, so next up we will look at how we would use logarithms to solve exponential equations. So what you need to do with things like this is you need to isolate the exponential expression. And then you take, if you have a base of 10, you take the common logarithm on both sides. Otherwise, you take the natural logarithm on both sides, any base other than 10. So then you simplify using the following, one of the following properties. So if you did common log on something that had a base of 10, one side of your equation would be log at 10 to the x, and that would just be x. Another property would be if you have a base of e, you'd have natural log of e to the x, and that would just be x. Now, if you had a base other than 10 or e, you would have natural log, let's just call it base a to the x. But you can use the power rule to rewrite this as x times natural log at a. And if your expression that's in the power is, more than one term, make sure you put parentheses around it. Okay, so let's check it out. And then, of course, you would solve for the variable. So let's see what we have. We have a single exponential term and then constant. So let's add 6 to both sides, and we would get e to the 2x is 38. So we have a base of e. So what we would do is we would rewrite this as natural log e to the 2x is equal to natural log of 38. So natural log at e to the 2x is just 2x. So 2x is natural log at 38. Dividing both sides by 2, we get natural log at 38 all over 2. So that is the exact answer. The approximate answer would be, go to our calculator here. All right, so we would just plug in natural log at 38. Don't forget to put your parenthesis at the end before you divide by your 2. And we get an approximate result of, I guess we can go 4 places. So that would be what? 1.8188. 1.8188. So we'll just put the exact result in the solution bracket. Okay, next up we've got, again, a single exponential. If I multiply both sides by 2, I would get 3 raised to the x minus 1 is 10. Now, if I evaluate the, which kind of log should I use? Good, I should use the natural log because I have a base of 3 on the exponential, and so I do not have a base of 10. It was a little tricky, right, because there was a, a 10 on the other side. All right, so here we go. We're going to use the power rule, right? So remember, we have 2 terms in that power, so we're going to put it in parentheses. And then we'll have natural log at 3 as a factor, and that's all equal to natural log at 10. Dividing both sides by natural log at 3, we'll have x minus 1 is natural log at 10 over natural log at 3. So then adding 1 to both sides, x will equal 1 plus natural log at 10 over natural log at 3. And then, I'm not sure what our author does, but we may need to get a common denominator of natural log at 3. So this is equivalent to natural log at 3 plus natural log at 10 over natural log at 3. And of course, you could write the numerator as a single condensed log. I mean, at this point, it just starts to get a little crazy. This would be equivalent to natural log at 3 times 10, which is 30, over natural log at 3 for our exact result. I would have taken any one of these 3 as an exact result. You'll have to check in the homework as to how you're supposed to enter it in. So our approximate solution would be, coming over here, natural log at 30 divided by natural log at 3 is approximately 3.0959. So our exact result is what I'll put in the set. I'll do the shortest one. Okay. All right, and then 10 to the x equals 120. So we would use the common log of both sides. So we'd have log at 10 to the x is equal to log at 120. We will just get x on the left side is log at 120. And our approximate result would be log at 120, 2.0792 it looks like. 2.0792. How you doing? Awesome. Okay, so moving right along. Now if you're going to use exponential form to solve logarithmic equations, basically you want to have a constant on one side. So you would have log base a at x is equal to y. And then you would use the definition of a logarithm to rewrite the equation in exponential form. And this method works the best when you have y as a constant and what's inside the log, is your unknown. So here we go. Log base a at x is equal to y is equivalent to a to the y equals x. Then you would solve for the variable, and then you need to really check solutions in this one, in the original equation, because we want positive values only. So we want whatever's inside the log, the expression has to be greater than 0. Okay, so let's check it out. So here, notice that we have a difference of logs. So we can write that as one happy log. So we have log base 3 at x divided by x minus 2 is equal to the constant 4. So in exponential form, we'll have 3 to the 4th equals x over x minus 2. Are you okay so far? So this is really cool, right? Because now we know that 3 to the 4th is 81. Oops. So if we just clear out the denominators, or just cross multiply, however you like to do it. We'll have 81x minus 162 is equal to x. So if I subtract x from both sides and add 162 to both sides, and then divide both sides by 80, we'll have x is equal to, we can reduce this to be 81/40. And then, did it say to approximate? It didn't say to approximate. What we'll do is we'll approximate so that we can, so 81 divided by 40. So 2.025 in decimal form. It's not an approximate, it's exact. So basically we have 2.025, and our original equation was this. So I'm going to say, you know, the way that you can check it is you could go through using common logs to check the whole thing. I'm basically checking to make sure that we don't get a negative in either one of the logs. So notice that the second term was of concern because it was x minus 2. So 2.025 minus 2 is positive, so we're good. Okay? All right. So there's our answer. Okay, so next up, we've got this one. So here we are. We have a sum of 2 logs. So what can we do with that? Awesome. We can write it as the product, the log of the product. And that's all equal to 2. Now what's the base of this log? Awesome. The base of this log is 10. And switching to exponential form, we will have this. So then we'll get 100 is x squared plus 21 times x. 0 is x squared plus 21x minus 100. Let's see, 25 and 4 is 100, and so this will factor as x plus 25 times x minus 4. So x plus 25 is 0, or x minus 4 is 0. So this would give us x is negative 25 or x is 4. So let's look at the original. Do you see negative 25 is extraneous because we can't have a negative in the log, all right, in either one of those. So this guy is extraneous. So the only solution that we have is x is 4. Okay? All right, so next up, using the one-to-one property of logarithms to solve logarithmic equations. So here, you want to express the equation in the form log base a at m is equal to log base a at n. So this form involves a single logarithm. Can't talk. A single logarithm whose coefficient is 1 on each side of the equation. So you use the one-to-one property to rewrite. So log base a at m is equal to log base a at n if and only if m equals n. So then you solve for the variable. You check the solutions in the original. Include in the solution set only values for which m is greater than 0 and n is greater than 0. My cat's playing with the cord for the mic. All right. So here we go. We've got so notice we have two logs, and the first log expression has this 2 multiplying to it. So let's use that power rule to bring that in. So that'll be log base 6 at x squared, and then we'll have minus log base 6 at 64 is 0. So if we add, I know it looks weird, but if we add log base 6 at 64 to both sides, then we'll get log base 6 at x squared equals log base 6 at 64. So what must be true? We have a single log on each side. They're both base 6. The coefficients are 1. So therefore, we equate the inside of each log to each other. So x squared is 64. So if we square root both sides, we would get x is equal to plus or minus 8. But if you look at the original, negative 8 is not going to work. So we have to exclude the negative 8. That one's extraneous. So the only solution we get is positive 8. Okay? All right, so the next problem we have is this guy. So here we go. They all are common logs. So let's just leave the one on the left alone. And this guy, it's a sum of 2 logs with the same base. So we can write it as the product of the 2 logs. Okay. So what's going to happen? We have the same log on both sides with coefficients of 1, so we can equate what's inside the logs. So we'll have 5x plus 1 is 4x plus 6. Subtracting 4x from both sides and subtracting 1 from both sides, we get x is 5. X equal to 5 is not going to violate anything here. And so we're good. All right, so next up. This time we're going to go ahead and use our graphing calculator to solve. So the way that, 2 ways you could do this. You could get 0 on one side and find the zeros, or you could just graph the left side and then graph the right side and use the intersect command in the calculate menu to solve. That's how I'm going to do it. So here we are. So we have e raised to the 2 times x on that side, and then on the other side we have x plus 2. Let's graph them. I'm going to go to the standard zoom and see what it looks like. Okay, so let's zoom in so we get a nicer picture. And I just want to make the y a little higher. So I'm going to make the y max 3, I think. And I think it'll be just perfect. Yep. Okay, so what we're going to have, that's our graph. And if we go to second, calculate, intersect, then you have to be near the intersection point that you want. So we're going to go closer here. So you click on the first graph, the second graph, and then go through the guess. And so this is what we get. And then we'll do the next one. And we'll have, all right, enter, enter, enter. And we get our second one. Okay, so, and then let me just put the y equals screen so you can see what I entered. Okay, so we have our solutions. So it rounded to 2 decimal places. We have x is -1.98 and 0.45. And you're done. Okay? All right, so next one, natural log at 2x is equal to -x plus 2. So there's our left side, and then, oh, it's almost the same. Let's go second, insert a negative, and we'll graph. Okay, so that window looks pretty good. So let's go to second, calculate, intersect. Enter, enter, enter. And here we are. And I'll put my y equals screen so you have it. I'll keep it over there. Okay. So we'll put our solution, just one solution this time, and it was at approximately 1.16. Okay, this one's going to be a little bit of a bear. Let's do a little work on it. So, you know what I would do is let's add this log to the other side. Notice they're different bases. So we cannot use any of our log properties on them. So we will have on the left log base 2 at x minus 1. And on the right we'll have 2 plus log base 6 at x plus 2. Now remember the whole change of base theorem. So it was log base A at m was equal to log b at m divided by log b at a. This change of base. So what we're going to do here is, I'll just use natural logs. So this guy will be natural log at, good, x minus 1 divided by natural log at 2 is equal to 2 plus, now what will log base 6 at x plus 2 change to? Awesome, natural log at x plus 2 divided by natural log at 6. So now that's what we'll enter in on each side. So here we go. All right, so natural log at x minus 1, and then divided by natural log at 2, and then this guy will be 2 plus natural log at x plus 2 divided by natural log at 6. Okay, so it looks to me like we're going to have to change our window. Let's go zoom standard and go from there and see. So, looks to me like we can go to, let's do 0 to 15 on the x, and maybe negative 2 to 6 on the y. I don't think we need to have it be so high. There we go. We're getting there. I'm going to extend the x a little more to the right. I'll do 20. I think we're good to go. Perfect. So we just have the one point of intersection again. So second, calculate, intersect. And we've got it. So here's the graph. And then here's what I entered in for our y equals. Okay? All right, so our solution is approximately 12.15. All right, so next up, and again, I apologize if you've got the first edition, there's a typo here. This should be log base 2. So solve each equation, and basically we're going to do exact solutions, and then we will also round to 3 decimal places. So here we go. I have a difference of 2 logs. So we get log base 2 at 3x plus 2 divided by x, and that's all equal to 3. So what should I do here? Awesome. I should switch this to exponential form. So 2 cubed is 8, and multiplying both sides by x, we'll have 8x is equal to 3x plus 2. And then taking away 3x, we get 5x is 2, and x is 2/5. Okay. So that's, actually they'll both be exact. If you write it in decimal form, it will just be 0.4. Okay, what about this guy? All right, so let's start out by multiplying both sides by 2. So we'll have e to the x plus e to the negative x is equal to 6. I just multiplied both sides by 2. So now we'll have, if I rewrite this as e to the x plus 1 over x equals 6. My apologies, 1 over e to the x. 1 over e to the x. And then if I multiply everything by e to the x, let's see what we get. E to the x multiplied to itself twice is going to be e to the x squared. So remember, you have to distribute it to both. E to the x times 1 over e to the x will just be 1. And on this side, we'll have 6 times e to the x. So we have something that's quadratic in form. So if I get everything on one side, this looks messy here, then I can use the quadratic formula, right? So if you need to make a u substitution, you can. But basically what will happen is, we're going to need some room over here. Basically what will happen is we're going to get e to the x equals. So it's not x equals, it's e to the x equals. And so we'll have, that's the opposite of b, so the opposite of negative 6, plus or minus the square root of b squared minus 4 times a is 1 and c is 1. And that's all over 2 times a. So e to the x equals 6 plus or minus, that'll be what, 36 minus 4 is 32 all over 2. So e to the x equals 6 plus or minus, 32 is 16 times 2, and the square root of 16 is? Good, 4. So we get 4 root 2 all over 2. So e to the x is, I can factor out a 2 from the numerator, and I get 3 plus or minus 2 root 2 all over 2. So these 2's are going to divide out, and you get 2 expressions for e to the x. So e to the x is either going to be, I'm going to go over here. I have room. E to the x will either be 3 minus 2 root 2, or e to the x will be 3 plus 2 root 2. So if I evaluate the natural log of each side, I will have x is equal to natural log at 3 minus 2 root 2. But I need to make sure that 3 minus 2 root 2 isn't negative. So let's see. So 3 minus 2 times the square root of 2 equals, okay, it's fine. It's positive. So that answer is fine. And then doing a similar skill over here, we'll have, actually, sorry, I'll just do it up here. Natural log of e to the x is equal to natural log of that side. So this is just x equals natural log at 3 plus 2 times root 2. So those are the exact results. The approximate results will be so we have natural log at 3 minus 2 times the square root of 2 equals negative, I think it said 3 digits, right? So negative 1.763. And over here, we'll have, so I'm going to do second inner and then just change the sign in the middle. Or positive 1.763. Okay? Alrighty. And guess what? That wraps it up for today. All right, so have a wonderful day, evening, morning, whatever time you're watching this, and I'll talk to you soon. Bye.